Wondering if you can hear me and you can see the screen.
Yes, of course. You are audible and visible. Good.
Perfect. Thank you very much to all the dignitaries for the welcome and a very pertinent information about power system. It's rightly said that power system is dramatically changing, very critical to the current environment, and of course very necessary in almost all fields. We can't live without electrical energy systems and essentially power systems. So let me talk about what do I see as the future of the power systems. But before I say future, let me tell you, it's very difficult to predict, especially about the future. That's one of the sayings. But anyway, I'll try to make an attempt. But before I say, I want to give credit to my research team. If you see here, these are my PhD students, and they have worked incessantly in all these areas, which I'll try to present in a brief. And I'm very grateful that I have been given a chance to work with these bright minds of future, and these are the ones who are going to change the world in coming years. So thank you so much to each one of my students, and also several undergraduate and postgraduate students who have been invaluable in disseminating a lot of hardware and the software simulations and analysis. All right. There's the staff profile I have. So there's a lot of papers in this, and if you are interested in any of the topics further, please visit them. There'll be detailed papers there, and I'm usually available on my phone or the Zoom. We can have further discussions on any other topic which you want. Right. So. There's a bit of a
please stop your mic. Please, I think some noise is coming. Please stop your mic.
Mute for all. Okay. All right. So let's start. So modern power systems. So if you see what power systems is, most of you know that traditionally you can generate the power from the. All right, there's okay. So you generate the power, and using long transmission lines, you serve a load center. And apparently, these are very nicely controlled by SCADA systems using an EMS, energy management system, by the grid operators, the guy who's sitting here. Now, this is a traditional power systems. If you see, the market has been introduced 20 years ago in 1995 across the world. And what happened there was you distributed the power systems into 3 different sections. GenCos, or generation companies, transmission companies, and distribution companies. However, nothing much has changed from a distribution perspective. The individual in the distribution side still don't have a lot of power to change their consumption pattern, but also their electricity bills. Now that gives an incentive for a lot of these distribution companies, and sometimes customers, I should say, to install their own generation systems. So sometimes they will have their own diesel systems, micro turbines, sometimes gas turbines for their captive power plants. Sometimes they also, in some of the buildings, you would see cogeneration, where you have a cogeneration or a tri-generation, where you have a HVAC combined with the local building powers. What has changed recently? When I say recently, perhaps 10 years ago, there's quite a bit of wind generation that coming into the system. Now, this was a humongous change for a system operator, because all of a sudden the coal plants were turned down or ramped down, and the integration of the wind actually challenged the operators to be wary of the ramp up and ramp down events, especially when the wind was picking up in the night and when wind goes down in the morning. Also, the problem was In the night, there is a less demand. So a lot of generation got turned off, or perhaps or in a spinning reserve capacity, to ensure that when the load picks up in the morning, it can ramp up. So there was a bit of a wear and tear issue, but still the wind penetration was up to 5 to 10% in most of the ISOs. When I say ISO, most of the systems, and it was okay. What happened in the last 5 or 6 years, if you are keeping an eye on the power systems, is these photovoltaic systems. Now, you might say, what 5 kilowatt system or 10 kilowatt system in a rooftop can do? Well, the thing is, it's just that there are too many of them. Think about 10,000 customers each installing 5 kilowatt system. You're looking at now gigawatts of systems. And that's what the problem is, especially in Australia. What we saw in Australia in 2009 and 2010, when there was an incentive for every homeowners to install the photovoltaics into their roof and get the feed-in tariff, FIT they call it, feed-in tariff. So there was a huge incentive for every house owner to install the systems to get or perhaps reduce the electricity bill. Nobody envisioned that 5 years later, these distributed solar will create a problem. The another dimension or challenges what we are seeing now is the addition of photovoltaic, of course, but plug-in hybrid electric vehicles. Now, plug-in hybrid electric vehicles have been integrated a lot in the United States, and they're coming in a huge wave in Europe. Australia so far has not been affected by PHEV integration yet. However, there is a concern from grid operator that all of a sudden, when this load kicks on at 6 o'clock in the night, there will be a peak demand problem which need to be managed. And hence, there's quite a bit of an emphasis on demand management. That means that how do you manage this demand? How do you scatter the peak so that you don't have to build additional asset to maintain the voltages and the network congestions when all the customers will turn on their PVs, PHEVs or EVs. Now, there is a bit of research talking about a substation. The substation should talk to each other and ensure that the local problems are resolved. Very easy as said than done, because oftentimes you would need a supervisory control to dictate these substation intelligent controllers. So we call it a master slave problem, and that requires a bit of a management. And hence there is a bit of a research on DERMS system, if you have heard of, Distributed Energy Resources Management Systems, DERMS. So a lot of companies like ABB, Siemens, and some of the local utilities are also working on designing these DERMS to manage the upcoming surge of electric vehicle load, and also what is already happening in the daytime with the photovoltaics actually reducing the load. So the problem has become humongous, because of daytime you see a very less load, and the evening you're gonna see a very high load. Coming back to distributed solar PVs, what is the problem with that? Now, as I told you, when all the customers, when I say customers, individual homeowners who want to get rid of or perhaps control the increasing price of electricity and reduce their bills, they want to install 5 kilowatt system, up to 10 kilowatt system in their rooftop if available, so that they don't have to worry about the bills. It's just that there are too many of them. At the moment, you are looking at 9 gigawatt of distributed solars. Just to give you a perspective, the Australian system is around 40 gigawatt. 9 gigawatt peak is a huge amount of solar in the distribution system. So what are the problems? Already all the utilities in different states in Australia are reporting issues such as over voltage complaints, inverter setting problems, power quality problems. In the LV feeder, when I say LV feeder, is basically 230 volts and single phase and 440 volts three phase. There's a quite balancing because these photovoltaics were not designed to feed in, or perhaps the network was not designed to feed in from this distributed solar in a uncoordinated manner. So they are creating a lot of unbalanced problems. Of course, there is a thermal capacity problem because um, sometimes the generation from all the consecutive or neighborhood solars becomes so high that the feeder is congested, and because of a very low load in the daytime. Similarly, you problem because of tap setting. Oftentimes, the tap settings were on a manual control, where or automatic control sometimes, but these controls are time-based setting. That means at 6 o'clock in the evening, the tap setting will change because they know that the peak load will come, and you improve the voltage in the distribution system by using tap changing transformer. However, now the problem is otherwise, because very low load, and that means a very high voltage in the daytime. So now you have to actually lower the tap to control the voltage. Easy for one day. Think about it if it does every day, every day, manage. And there are a lot of tap changing transformers. So there's a lot of issues in a low voltage and a medium voltage grids. When I say grids, means distribution grids. Now you might say, okay, all right, we can manage it. Distribution system operators, or we call it distribution network providers, is their problem. So as a power system, we should still be fine, right? Well, hang on. Now we're looking at large-scale photovoltaics. What are large-scale photovoltaics? Now we're looking at 100 megawatt of solar farms. That's huge. And these are photovoltaics, not concentrated solar powers. Now, the problem with the flickers and whatnot, with the cloud transients and other issues, but the humongous size of this solar farm is going to create another operational challenges. Think about a cloudy day. Now you have to somehow make up for this 100 megawatt from the grid. Remember, the coal plants have a problem. They can't ramp up and down so easily. So either the business owner of the coal plant will say, give up. All right, I can't recover my money. Sorry, I'm closing down. And that's exactly what is happening in a lot of countries, not only in Australia. The coal plant operators are saying that, because there is lack of demand, I'm not able to recover my money. Sorry, I have to retire early. Not only that, the new coal plants are not being built because they don't have a PPA. PPA means power purchase agreements. And also the finances. They're not getting finance because they cannot justify whether they will be in the business for next 20 years. Can you see the cumulative problem here? Because of the intermittent generation. They are sucking up a lot of load. So from an operator perspective, now when I say operator here, I'm looking at a EMS who's managing the EMS. What is EMS? Energy Management System using SCADA. And he's sitting at a load center or an operation center, depending on the country you call it. In the United States, they call it independent system operator, who takes all the bits from the generators and the load centers and clear the market and ensure that not only the financial side, but also operational side is taken care of. That means the load is always matching the demand. The generation, and the frequency is maintained at 50 hertz or 60 hertz, depending on the country. In Australia, that's the job of an AEMO, Australian Energy Market Operator. So they are seeing this problem. If you can see the curve, you can see from 2015, the curve was here. It's still called a duck curve. There's a morning peak and there is a bit of a reduction in the peak in the daytime, and there is the evening peak. This is the demand I'm talking about. Now you see, as we are progressing in the years, in 2019 the peak is getting lower, and they're predicting in 5 years time this is going to be even lower, and that's going to be a problem. If you see in the midday time, there's a huge reduction of load. Now remember, those who know power systems, they know that the network has to be built for the peak. That means you have to still manage your network at this demand. But in the daytime, the demand is almost half. So what's going to be the problem? The problem here is how we're going to manage this ramp down effect and a ramp up effect. There's a very steep increase in the demand. They're predicting is going to be more than 3 gigawatt per hour. Now you can see, as a power system engineer, that's a lot. That means there are going to be more gas plants. We need them. Otherwise, we'll not be able to manage this much amount of ramp capacity. Or more wind farms, or who can actually ramp up quickly, but with batteries, of course. Similarly here, ramp down effect. So I talked about batteries. This comes here. Now, what should be the size of the battery and where it should be placed? That's the problem. Now, if you see what has happened in the past, there are few smaller batteries, like 20 megawatts flywheels were tried. Now, these are not batteries, but this is a magnetically controlled superconducting material flywheels, and this is 20 megawatts in Stephenson, New York. That was, I think, in 2010 or 2009. And then in a similar time frame, there were some battery storage systems installed in US for 1 gigawatt. And that time, people were saying, yeah, there'll be 1 or 2 of them. There won't be a lot of them. They are too costly. $50 million. I mean, it's a lot of money. And such a big battery. Batteries are very expensive. So yeah, this is one off. But what is happening now in Australia? 3 years ago, there was a blackout. And all of a sudden, Elon Musk comes and says, 100 megawatt battery in 100 days, otherwise free. And you know what? He installed 100 megawatt of battery within 100 days. And that was a big wave of innovation in terms of not only money, but also the benefit these batteries can create or help these operators to manage the grid. Over the last 3 years, it has saved almost more than millions of dollars in ancillary services. So it is trying to control the frequency of South Australia, and this battery is next to the wind farm, and it's bidding in the market. Having seen this experiment, apparently it is going to get extended from 100 megawatt to 150 megawatt. Of course, there's a business need and a viable reason to do that. Seeing this model, a lot of other battery energy storage systems are installed in Australia. In Ballarat, another one, Coonawarra, another one, and you can see in the for 30, and yeah, a lot of batteries are coming to the system. Now, what we see, the customer engagement problem. In Australia specifically, because of the geographically dispersed region, the population density is very less and the power prices are very high. Customers are complaining, you're doing so much about renewables, what about my power prices? What about my bill? And what can we do to give customer the power to be able to control. These individual customers can talk to each other and reduce the demand and control the bill. There is called repository power. This actually gives you direct control from your iPhone. You can set on an automatic mode where you can control battery and photovoltaic and build the market. Is a market for incentives. Control your photovoltaic time, use your bill. Not only customers, is a remote community sometimes, but also those who are in suburban area thinking, why should I pay huge bills for my consumption at the local level? And a lot of communities or councils are agreeing on instability based. In Western Australia, there's a community power bank. I think if I receive 200 kilowatt battery. So based on the given suburban area, there's quite a bit of photovoltaic. They say that, okay, you know what? Why don't your photovoltaics charge this battery in the daytime, and we are going to refund you the money. We're going to pay you for how much you charge the battery. And in the night time, these batteries will supply the power. All of a sudden, reducing the night peak. Win-win situation for customers. They're getting paid. Councils, they don't have to pay the huge charges in the evening time. And system operator, because now they don't have to worry about the management or the network augmentation because of the increase in the load in that area. So you see all facets of new power systems. Now, some people use the word smart grid. The idea behind the smart grid was actually to enhance the grid reliability and control, reduce the production cost. When I say production cost here means that the generation cost, which is being touted as one of the ways why you need to pay the bills. What about the cost when it comes from renewables? Apart from the installation cost or CapEx, which is a capital expenditure, the OPEX or operation expenditure for these renewables are almost zero. So in 5 years or 10 years time, the production cost is going to be significantly less. So, and we are actually improving the efficiency of the system anyway. So grid is becoming smarter. But what we engineers see how it's going to happen. So from a generation side, there's a chat. Let me see. Just write down. Okay. All right. Not to me. Do the bulk batteries have different chemical composition? Well, good question. So at the moment, no, I think that they are lithium ion based, but they are looking at flow batteries as well. So yeah, thanks for the question. The different utilities have a freedom to install different kinds of battery depending on their cost benefit analysis. A lot of companies in Australia at the moment are taking an easy route. Take a Powerwall. You heard of Powerwall? Tesla, Elon Musk company. They give the Powerwall 10 kilowatt hour battery for $10,000 and 10-year warranty. And easy. And then you have, if you're a business owner, install 10 of them, all of a sudden you have a pretty good independent storage. All right, another question, write down your question. All right, okay. I don't mind if there are questions in the middle. I don't mind, it's okay. But yeah, that's fine. Let me continue. So from the generation side, now all of a sudden, because there's quite a bit of infeed from a distribution, when I say systems, you will see PMUs, phasor measurement units on the generation side to be able to now sporadically control these generation or infeeds from DERs, distribution energy resources. and the wide area controls and management is going to get more significant in coming days. Transmission side, well, you would say that transmission is saturated. Why do you need anything else? Well, no, because of the infeed from these photovoltaics, we are seeing a problem in Queensland where QNA, which is a Queensland New South Wales interface or intertie, is getting overloaded sometimes for wrong reasons. When I say wrong reasons, it was designed to export the power from one area to another, but now it's getting import from another area because of photovoltaics. So there is an increased monitoring of these interfaces in coming years. And the idea is because if you do not monitor these interfaces, there will be a stability problem. Those who understand power system stability is the angles which oscillate against each other when you have a heavy transfer of the power from one area to the other. So, all right. On a distribution side, we're going to see quite a bit of demand response and smart metering. But what I see, the vision is in the next coming year, there will be a new market at a distribution level, like peer-to-peer market, where every individual will be able to trade with each other. Now, few trials have started, but this is going to come in a big way because the customers are huge. You have a huge market for that. And there's a problem in terms of managing the voltage and the current at that level, which is only visible to distribution side, not the transmission operator. All right. So these are the challenges. What are the opportunities? As a researcher, we always find out what's going to happen in future and try to address some of the problems from an engineering perspective. So this is what we did. We saw when the problem inertia was coming, where when you have 10 or 15% of wind power into the system, the coal generation is ramped down for the same load, or especially in the night when you have a load which is very minimal and the wind is at full blast. Now you need an inertia. So wind can supply a little bit of inertia. So we devised a controller called a fuzzy logic controller, which is a simple rule-based system which will control the power from the wind and the power from the storage or a cumulative battery using a 3-winding transformer giving to the point of common coupling. The actual measurements was frequency and DFDT, which is a change of frequency with respect to time or rate of change of frequency, which is ROCOF, ROCOF. And he actually designed this simple controller to modulate the power from the wind and the battery. So if you're more interested, please look at this paper. And yeah. So, and there's another way to look at the regulation problem. So if you assume that there are a lot of retailers and there is a bit of a transmission or sub-transmission system and a distribution system which is serving different homes, and a home is connected with a lot of appliances. So you can actually supply the regulation services. What are the regulation services, by the way? This is actually the way to control the frequency or supply to the change or the fluctuation in the frequency under contingency events. So you can have these retailers bid into the market and use the DERs from the distribution system to supply the services. In America, there are some cases where they are actually doing it already, where they are actually having a contract with the building, for instance, and they modulate their loads or appliances and supply in a wholesale market. PJM, Pennsylvania, New Jersey connection, and Maryland, and this is ISO, Independent System Operator, and they are doing quite a bit of regulation services using a similar concept. So we wrote a paper about the conceptual way of dealing with the not only retailers but also several aggregators who would be on a lower level than retailers and try to manage the customers. So this is an algorithm where the retailer will talk to the aggregator controller, and aggregator will take different attributes based on the customer information. And it will calculate what is the probability of a given circumstance, given appliances to be able to serve a given response. And oftentimes you can categorize them into most preferred, not preferred, or unresponsive probabilities. So essentially the different kinds of loads will have different margin to be able to supply or absorb the power at a given time. And this is calculated probabilistically, and hence you dispatch the signal in a given time. Uh, you calculate the signal in a given time and operate in this horizon, time horizon. Details about that is given in this paper. So now you can still say that it's a passive control because the customers are not actively involved. They're just given, okay, I want to control your load. This is a contract, 3 months or perhaps a year, and you'll be paid, say, $10 or $20 or $100 in a quarter or in a year. It's a coupons which are given to them. That's it. But there's no active engagement, and the rewards are very minimal. So then we come up with an idea of a demand response of these appliances using customer reward, where customers are actively rewarded for how much they are contributing to a given congestion. Because not all customers are equal, like not all loads are equal. Those customers, bulk customers, for instance, a shopping center, or someone who's doing a business from his home, he has a big load. Now, if he applies for this customer reward, his load modulation will change the voltage and the current in the grid to a higher degree, and hence he should be paid more than his neighbor who's probably have a smaller capacity. So you can actually do that using customer reward. And another way to look at is where retailers risk-aware trading framework, which is done by Noor, where you have a bi-level optimization of not only the transmission operator doing optimization and controlling the load at the lower level to try to minimize the generation cost, but also at another level, which is a lower level where all the aggregators are trying to reduce and do the optimization at their level. And there's a very nice game theoretic approach, and the papers are written. Please go through them if you're interested. So this is where all the retailers are directly talking to the aggregators. So we were talking about the customer reward mechanism. The idea here was to actually control the overloading transformers at a given feeder or a suburb, and eliminate the voltage violations to control the load. So essentially, we are assuming that the smart meters will be there, and these transformer controllers will be able to talk to the smart meters. Quite a bit of trial happened, and a very successful trial happened in Australia in Ausgrid, which is a place in New South Wales, and they saw that the customer reward mechanism is pretty helpful. Also, we did some research with social scientists about the amount of reward we pay to the individual residential customers, and that was a trial done in Magnetic Island, in one of the islands in Queensland up north, and that was also very successful in terms of being able to defer the investment in the network by differing or leveling the peak. So these are the simulations what we did, and we were able to chop the voltage using our intelligent controllers. The key was, how do we actually define the reward? So what we did was the shifted energy has a component, but also the voltage improvement. So how much voltage you are improving in a given feeder. So suppose you modulate the load, those who are power system, they would realize immediately that if you are towards the end of the feeder, even a small change will bring quite a bit of improvement in the voltage compared to the customer who is near the substation, because his voltage is stiff. So you should be rewarded for how much voltage improvement you're doing, and these voltage are improvement can be counted in every 5 minutes or whatever frequency you want to count as. The constants alpha and beta are decided by the utilities based on their curve and how much they are able to benefit from the network augmentation. The details are in this paper. The another idea what we were talking about is the real-time pricing. What is that? Now, at the moment here, the customers are getting a constant price or a more or less constant price because they are not able to see what is happening at the wholesale level and what are the environmental effects. When I say environment, means how the prices are changing based on a peak day or a summer day or a winter day or a cloudy day or a windy day. Now, if the customers are given this real-time price, which reflects not only the electricity price at the wholesale level, but also the network constraint at the local level, all of a sudden, you can actually improve the demand response capability. The idea was, how do we design that signal? So we call it as a real-time pricing. So where it has the component of all these three prices and the customers are rewarded accordingly. You can see that quite a bit of focus of this research is on the customer side because let's face it, customers have to be happy. And we are trying to do the best so that they can reduce the price. And this is about individual house level. Now we are envisioning that this will be controlled by HEMS, Home Energy Management Systems. What these are automatic controllers, PLC based. What is actually they're doing is they're connecting using a smart plug, using Zigbee or any other protocol you want to use, and talking to these individual appliances and work in a daytime to optimize when your dishwasher should be working, when your battery should be charged, and when in the evening time when you come, when you should be discharging your batteries, which appliances you should be using. Dishwasher should be used at the night. Clothes washing should be done in the daytime, in the weekend, something like that, which is a smart controller. So there's a bit of papers what we have written, and there's a very nice algorithm what one of my students has developed is a differential dynamic programming based home energy management scheduler, which is recently published in one of the transactions. So let me see, there was some questions if I remember. Oh, it went away. Okay. All right, it's gone. So, all right. Okay, I'll address to the question because I can't see. Anyway, so the purpose was, okay, let me see. There's a chat. You write down your questions or ask in the middle, no problem. Okay, okay. All right, no questions. Coming back. Yeah, so I told you about this four thing: demand response via customer reward mechanism, real-time pricing, home energy management system, and a DR in ancillary services market, essentially trying to deal the problems in the distribution system. Another problem what you are finding out is when you have this photovoltaic injection, as I told you, is about high voltage in the daytime and low voltage in the nighttime, which is completely opposite of what we need. We need a good voltage in the daytime and a low voltage in the good voltage in the nighttime because we are at home and we need to use our appliances. And here, voltage can be hitting the limit, but we don't want to burn our appliances as well. So, but still important to stay below the limit. But we don't want low voltage here. What is happening with the high voltages is a lot of inverters are turning off. So even though the customers feel that they are supplying power to the energy, to the grid, but they're not, because inverter has a control of over voltage protection. So the moment the feeder voltage goes up, inverter trips. And the customer feels that, oh, I'm happy, but I'm getting only $30 off. Why? Because you're in a place where the voltage goes very high and your inverter is off. And there are a lot of other problems. We wrote a good review paper about all the problems what grid-tied rooftop small-scale photovoltaic generations are causing recently. So this is the data from one of our distribution utility, and you can see that the voltage is all over the place. You can see that this is the way the voltage should be, and you can see how much high voltage these feeders are coming. facing on a regular basis. It should be 240, and the voltage can go up to 254. So essentially the idea is, as I told you, farther down the line, this is all the power engineers know, this is a typical formula for calculating the receiving end voltage when you have a stiff sending end voltage and the injection from the given feeder. You can see that the farther away you are, higher will be the voltage. So what we devised was to have a droop-based battery controller, which work in conjunction with the PV inverter. And this was a highly cited paper we wrote a few years back. The idea was to actually somehow arrest the increase in the voltage before it goes really bad. So the moment it starts increasing, you see the droop and you start charging the battery. The moment it goes to a certain level, again designed by the algorithm, there you use the reactive power if available. And then that way you can limit the size of the battery, because if you store everything in the battery, then battery cost will be humongous, and not every customer can afford the high cost of the battery. So when you work in conjunction with the reactive power absorption from PV inverter as well as droop-based control of the battery, the sizing will be less of the battery and you can still maintain the voltage within the limit. In the evening, what you do is supply the battery and also the reactive power to improve the voltage. The moment you improve the voltage, all of a sudden reactive power problem will be solved and system will be better. Now recently we realized that these battery controllers and the inverter controllers would have to talk to each other. So it's a very nice paper what we wrote about what happens when there's a delay in the communication from the central substation controller to these individual controllers. So that's another problem, paper we found out. And we say that the predictive power compensation control will work better if you have a delay in the communication from the central controller to the slave controllers. Now this is for the customers who have batteries and photovoltaic. Some of the feeders do not have that privilege. Very remote area, people do not have a lot of money to be able to install these devices. Now there comes STATCOMs. So these STATCOMs can actually move very fast and control the voltage in a distribution side. So, and that's what we have been working with some of the local utilities here who are working in a suburban area and be able to control the voltage. So this was a trial. If you can see phase A, phase B, and phase C on, and you can see that the voltage was here. All right, and when they're off, the voltage is going crazy. When it's off means the STATCOMs are off. Okay, so when the STATCOMs are off, one voltage is very low and the other voltage is very high. You can see that the dotted lines. And when the voltage, when the STATCOMs are on, they are with the band. So what major problems these STATCOMs, and we did the sensitivity analysis, and we have a couple of papers to be able to help the local utilities to control and put the STATCOM where it is optimal. You can see that it is an unbalanced injection. So you can see when it's off, there's no reactive power injection. And you can see the reactive power absorption and injection from phase is significant to reduce the unbalance in the voltages. And it's a dual thing. So not only it reduces the unbalance, but also puts the voltages of all the phases in the right band. So coming back to, I hope I'm okay with the time. All right, so coming back to this managing variable renewables. So we are seeing that the problem is gonna be from generation and transmission planning for long term to a day ahead, intraday, and balancing. And we have worked in almost all the areas. Now, what is required now is perhaps for academics like us to talk and engage with policymakers on a regular basis, because system is changing very fast, and if we do not do it appropriately, there's going to be a significant problem in the coming years. When I say problem, is the cost to the customers is going to be humongous. There will be stranded assets, there will be money invested in the projects which probably may not be the smartest way to control or manage a given problem. So there's a variability issue what we need to deal with, there's a flexibility issue we need to deal with, and there are some long-term planning issues what we need to deal with. So on a distribution side, of course, but what happens on the transmission side? There's going to be quite a bit of probabilistic analysis required. Why? Because there's quite a bit of variability from these DERs and the wind resources, because of now we are dealing earlier. Power system engineers were able to deal with the uncertainty from the load. So you model that as a stochastic load, integral of the white noise or whatnot, and then still you can have a bit of certainty of where the load growth is and hence where should be your transmission lines. But now you're having a generation uncertainty as well as demand side uncertainty, and then it becomes a bit of a issue. So we try to propose a couple of ideas on probabilistic contingency analysis to be able to come up with the optimal policy, if you were to say, to maintain the stability of the system on a bulk level. What we are envisioning is a lot of SVCs with the power oscillation damper will be required, and these SVCs will be playing both roles, not only to support the voltage but also to damp the oscillations. PMUs will be on steroids, if you were to call it, and they would be working very hard to maintain the dynamic visibility of the interface. So we had a project working with the local transmission company where they were looking at the intertie issues and the stability problem created due to the flow in the intertie. So we proposed the modulation of the SVCs and the power oscillation dampers. I think a couple of papers are there. That was in probably 5 years ago. So this is what I see the system future is looking at. It's you have at upper level operator, transmission system operator, and distribution network providers, and you're going to see quite a bit of services, if you were to call: frequency control, demand side management, wide area control, and market prices spike. These are the 4 services that will be sold to these individual customers, and there will be quite a bit of interplay between commercial customers, industrial customers, small scale storage, residential customers, and the rooftop PVs and small appliances. So at every level, there will be new players coming and serving and providing services in these 4 ways to these network providers. And this is how they're going to be dealing the future power systems. Yes, that ends the question. Thank you so much for listening, and we'll welcome any questions.
Thank you, Adendra Mishra. Dr. Adendra Mishra, thank you so much for your wonderful presentation and its piece. Thanks our participants, their attention. Now let's start the interactive question answer session. Dear participant, please ask.
Sure.
Don't hesitate, ask directly or just write down in the chat box preceding your name and affiliation. I will pass it to our speakers. So this is the question answer session. We already have a couple of questions. One question is from Raji Chuet. He asked that in Bangladesh, where demand is always more than the generation, will the customer reward scheme works? This is the question. Demand is always more than the generation. So will the customer reward scheme you discuss it works or not?
It will work more than anybody, because now there's incentive for the utility to actually defer the demand. Because if they don't, they have to build additional line, or they have to do the network augmentation in terms of a new transformer or rewiring on a given feeder. So yes, they should do it. Now it's about the incentive to these individual companies, and perhaps that's where there is a policy issue. If there is you guys are professors, talk to the policy makers and say, okay, you know what, rather than investing and paying utilities so much of money as a capex, we can pay part of the money to this so that it can pass to the customers and modulate the demand. So it is possible.
Thank you. I think the question has been answered. So another question from Dr. Mahmoud Abdul Mateen. His question is, what is the maximum percentage of variable power mix like solar and wind can be allowed in the national grid? Bangladesh has target renewable energy mix 17% by 2041. Should there will be big problem, how might be solved?
Correct. Now, initial studies by Nicholas Miller, if you know, in 2011 or 10 or 11, they talked about, they did a study about how much integration is possible when you have this intermittent generation. And they found around 30 to 40% of wind can still manage the stability problem. Now, this is in general. Now, it all is sometimes you got to see locally what are the issues.
Okay, thank you. So another question from Fahim Mahmood. He asked, Professor, as I understand, keeping the price at a reasonable level to keep the customer happy is one of the main challenges of the power systems. I was wondering, is contingency a problem, like keeping the grid functioning in terms of outage? Are there databases available such as voltage level, power flow, etc., based on which contingency occurrence probability can be predicted? Can this data be used in existing machine learning algorithm to help assist the operator?
Brilliant idea, brilliant idea. And I think data are available. Yes, you got to talk to the utilities. They have quite a bit of data from the last 20 years, which fader is recurring, having a problem. And oftentimes they solve a problem given on an issue. They don't do a lot of maths or mathematical analysis. But yes, definitely go talk to them, and yes, the problem can be solved, and perhaps that's the right way. Now, the question is whether contingency a problem. Well, power system has to be modeled in a way so that n-1 is 100% servable. Means that if one contingency happens, you should still be able to serve 100% of the customer. Now, there are exceptions there. Exceptions means there might be an area where you cannot serve 100% load, and then there's a special protection system schemes that are installed. So yes, you have to look at a given area and see what are the utility procedures and operations at that point, and then solve
it. Yes, one more question from Naim Rahman. In Bangladesh, power demand increase day by day, but we have cost and land shortage. So is there any way without renewable energy to solve this problem?
Oh, that's a tricky one. Well, nuclear energy can be one of the option, but it's quite a bit of resistance from government specific. There are issues, but it's very concentrated energy, and perhaps it's more of a policy question.
Okay. So Akram Haq from Premier University, he asked, during high voltage generation of PV during daytime, can we use back converter which can reduce this to a usable limit?
Correct. So the current inverters at the moment are not smart. They call it dumb inverters. Dumb inverter means that they just switch off given a protection setting. Now you can have a centralized controller. We can talk to these inverters and limit the injection of power. But tell me, is it a smart thing to do? You are limiting the green energy. Why not store it? And hence comes the community-based storage, which is a cost-effective option rather than limiting the green energy injection to the grid.
Thank you. One more question from Dr. Mofazzal Hossain from ULAB. Do you think the DC transmission and distribution system may solve the frequency and phase related problem? May we migrate from DC to AC gradually, because nowadays most of the appliances are DC based?
Correct. Future all will be fine, but we are in transients. At the moment, we have quite a bit of AC appliances or AC system in place. Transition to DC will not be smooth. But yes, frequency problem will be eliminated. It's very easy to control. It's still far away.
Okay, thank you. So, is there another question from Gailan Ibn Wahid? Jailan Ibn Wahid. Is there any possibility to have AC power directly from solar panel?
The solars typically have DC, and there is an inverter which converts into AC. Well, I'm not expert in cell manufacturing, so I'm not sure, but I still feel that it's a photonic effect, and hence you'd rather have a DC rather than AC. AC requires an oscillation, which means there has to be an inverter to convert.
In solar cannot be AC. It
Correct.
will be DC.
Yep. Correct. There is no scientific, yeah, exactly. And that's why I said 10 years later, they might.
It definitely will be DC.
Yes.
Thank you, sir. Rishita Chakma, he asks how predictive analysis can help in demand side management.
Okay, good question. Now, what is a predictive analysis? You're going to see what is going to be the integration of DERs or what is going to be the demand in a given time. If you know the probability of a given occurrence in a given area, all of a sudden you can actually have a smarter decision rather than actually monitoring a given area. Now, monitoring, you can always do monitoring for everything. The problem is the cost. And everywhere installation of smart meter would cost something. Who's going to pay for it, right? Second thing is, even if you paid, there is a customer resistance. They don't want to be monitored sometimes, and there's a free will, right? You cannot force someone to have a smart meter, right, in a free country. So there are problems there. So probabilistic analysis would help, definitely.
Thank you for your nice answer. Another question is, lots of a question is coming. So if I want to, my generator say 2 megawatt of my factory hook up with a 33 kV grid, what might be time for return of investment? Swissgear, systems, etc. There is a Bangladeshi industry is still re-rolling mills. He is a guys. He asked that if I want to, my generator, he has 2 megawatt capacity of on-site in-house generation, but all the same time he is also connected to 33 kV. What might be the time for return of investment of that generator?
See, it's a very good question, and let me tell you, it's not hard to analyze. What you need to do is see your demand, see your network charges. Sometimes you will have a connection or a tariff which will charge you for reducing a certain amount of megawatt or a kilowatt depending on your load. And what you need to see is perhaps what are the connection charges and if you can reduce the peak. So if you have a 2 megawatt of local generation, definitely your peak charges will be less. And if you have a battery with it.
Another question is from Abdullah MD Zubair. Sir, one of the main obstacles in large scale solar power generation is requirement of land, which is not available in our country. How can we maximize this utilization of land? What are the possibilities?
Yeah, it's a tricky one. Sometimes you may consider concentric solar power, which will require lesser land, and with the storage, which is a molten salt storage, you can get away with a more amount of power from a small land. Photovoltaics require a lot of land, and which may not be possible.
Okay, thank you.
Or another is offshore wind plants.
Right. Another question from Akramul Haq. Solid state battery are expected to have double capacity, taking the same space of lithium ion battery. So the community based storage will be more familiar. Do you think solid state battery will replace lithium ion battery as soon as possible, as high level of renewable are expected to be connected with the grid? Should we care about the huge impact on economics? So yes, this is the last question. I think we are taking too much question, and we are closing to our time. So
Nur Muhammad.
yes, please, sir.
Nur Muhammad is unmute. For previous last two questions, one is what will be the payback time for local generation. According to the Bangladeshi situation, roughly it will within 5 years. Money payback. And for the second question, there is no plenty of land to install photovoltaic system in Bangladesh. This can be solved by agro photovoltaics and floating photovoltaics and many other options. So the land problem and the land issue already solved. So I don't think so. The issue regarding cost and limited land is already solved for Bangladesh. And I have I want to take a suggestion from our honorable keynote speaker. Bangladesh has a master plan 2040 about 40 gigawatt coal-fired power plant, out of which at that time our maximum demand will be 56 gigawatt, and there will be more than 40 gigawatt coal-fired power plant, and majority this will be imported coal. Only about 1 gigawatt might be internal coal. So in that situation, can we go for more renewable energy mix? The government has set up 17%, but many of our engineers, they are demanding it should be more than 30%. Will it be viable for Bangladesh, 30% renewable energy mix in the grid?
Yeah, it's a tricky question. See, I'm not aware of the landscape, but options such as floating, as you said, agro PVs, or perhaps floating wind farms, offshore wind farms, but there is a water problem. I mean, the land and stuff. See, it's a tricky one.
Thank you. So I think we are closing question answer session. I'm taking one more question from Kamrul Hassan. The customer has IoT based solar system. Can they contribute to the local distribution in any way with minimum cost? IoT based solar system means or they have a smart meter feed-in tariff system. Can they contribute to local distribution in any way with minimum cost?
Well, see, it's a distribution charges depending on the size of it. Like in Australia, if you have a 5 kilowatt or less, is automatic connection. Between 5 to 30 kilowatt, you have to consult the distribution provider, and above 30, there has to be a system level study. So you got to talk to the distribution operator and see what are the issues, because there can be a voltage rise issues, which will limit your injection.
Thank you. Thank you.
Sir, I had one more question. Can I place it?
Yes, of course. Please ask directly to our honorable speaker.
Okay, sir, thank you very much for your nice presentation. Actually, I have one question. In your presentation, you said that in near future, the huge difference between demand in day and evening time will create problems of steeper decreasing and increasing ramp on the power system.
Correct.
Do you think that selecting a base level of power generation for the data for the average demand and for the peak demand for the peak, to meet the peak demand, segmenting the power systems into smaller power plants and connecting and disconnecting them step by step on the basis of demand will solve the problem.
Yes, very good question. Very good question, and it's a very relevant question as well. We call it multiple microgrids or microgrids. So you can isolate the systems and still be able to manage and reduce the ramp up and ramp down thing. But again, it's a case by case basis. You have to study the given area and see what can you actually manage the islanding or anti-islanding protection, what we call it microgrid. That's a bigger problem. Fault is a major issue in microgrids. You can always save the system for a short time, but if the fault happens in microgrid, sometimes it's not identifiable. There are smart algorithms to do that, but it's not foolproof yet. But again, there's a bit of a change in the shift or a paradigm in terms of planning. So of course it's possible. Of course, it's a lesser cost than over-investing in the network, but the details have to be figured out sitting in a given system and seeing what are the options.
Thank you, sir. Your answer is very effective, and I have understood the matter. Thank you.
Thank you very much.
Thank you, all of you. You guys really enjoy, and it is a great honor for us to have great speaker like Dr. Yatendra Mishra. Thank you so much for your wonderful presentation and speech. Thanks our participant for their attention. Now I would like to pass this event. We are closing to end. So webinar chair of Professor Dr. Muhammad Ahsanullah. Just he will, Dr. Muhammad Ahsanullah.
Okay, thank you.
Thank you.
Thank you very much. It's a nice presentation and an interactive question and answer session, and we benefited for the new arena of the power system, sustainable solution of the power system problems, and today's talk may open the eyes for the varieties of the routes of the consideration for the sustainable solution for power system problems. So I give my gratitude to the speakers and all listeners, and I give thanks to all for the participating in this event. And I say maybe in next we will arrange similar type of webinar, and I request to all to join again for the future events. And I give thanks again for everyone, and thank you. Thank you.
There is an appreciation certificate for Yatendra. Please.
Okay, we'll give appreciation. Please
so I'm
sharing
this certificate, and this will be discussed in the right time after finishing this event in any way. So everybody, please have a look. Webinar on Power System Certificate of Appreciation awarded to Dr. Yatendra Mishra in recognition of keynote speaking on future power systems, challenge and opportunities, signed from department. So it is a great honor for you and for us all as well.
Thank you so much. I enjoyed it.
And we expect again the Yatendra Mishra from in future for similar events.
Sure, always a pleasure.
Okay,
We researchers want to share our ideas, and you know what great opportunity it is to be able to share and have such a nice question and answer sessions. Beautiful audience, thank you so much for listening, and I hope I have excited our young minds to change the world.
Thank you. Thank you.
So one more thing is left. We will take a group photo. Just please turn on your webcam or camera. And another message is there will be a file like feedback, webinar feedback form. I will share it through email. So you will please just respond it and return back to me. That will give some encouragement how to the shortcomings we have, or what are strength or weakness, so that we can next time will fill up this point. So please turn on your camera and little bit smiley faces so that I can speak couple of shoot. Yes, from different. Yes. Thank you all. So that's it for today's session. Thank you, Atenta, Mr. again.
Thank you very much.
Yes.
Enjoy your day.
Thank you.
Have a nice weekend. Talk to you again. Bye.
Okay.
Bye.
Bye.